So isoparametric formulation, we are going to discuss about the isoparametric formulation. So the shape function is related with the global displacement and the local displacement. There is no doubt. So the isoparametric formulation is used to represent the curved boundaries. First one, it is used to represent the curved boundaries. Curved boundaries in which the geometric irregular boundaries are considered, and also the elements of high stress gradient can also be mapped with parent as well as child element. So the isoparametric means the shape function n1 is used to represent the geometry as well as the displacement. Represent the geometry and the displacement So we are using the same function to represent the geometry as well as the displacement. So those elements is called isoparametric elements. The shape functions defining the geometry as well as displacement in a particular element. Those elements are called isoparametric elements. The formulation is called isoparametric formulation. We have another formulation like superparametric formulation. So this is about the element in which more number of nodes are used to define the geometry compared to the number of nodes used to define the displacement. So if you take this type of boundary, initially this is used to represent the geometry and another 4 nodes are representing the displacement. So in addition to that, more number of nodes are representing the geometric variation, then the element is called superparametric element. So this 4 nodes representing the geometric variation. So here 4 and 4, 8 nodes are represented to describe the geometry. Another 4 nodes are representing the displacement. So more number of nodes are used to represent the geometry than the displacement parameter. Those types of elements are called superparametric formulation elements. The next one type is subparametric formulation. The subparametric formulation is opposite to superparametric formulation, in which more number of nodes are representing the stress variant, at which point the stresses are some boundaries having high stress gradient. Some boundaries are having high stress gradient. In those boundaries, we are considering more number of nodes than the number of nodes in the geometric variation. The number of nodes. This 4 node is enough for representing the geometric position. I am representing here a circle inside a square. Circle inside a square is representing the geometric variation. At the same time, the curved boundaries having 6 nodes representing the stress variation. So the subparametric formulation, the element in which more number of nodes are representing the stress gradient than the number of nodes describing the geometric variation. So I think you have some understanding about the isoparametric, superparametric and subparametric. Isoparametric, a single shape function representing the displacement as well as the geometric variation. It is called isoparametric formulation. So after this, we are going to derive the shape function for 8-noded rectangular element. In previous previous video, we have derived for 4-noded rectangular element. Here I am going to consider the 8-noded rectangular element. So there is no change in representation of epsilon and eta, and the first 4 nodes also same in case of 4-noded element. So this is 1, 2, 3, 4. The 5th node I am fixing at midpoint of each side. 5, 6, 7, 8. Now I am going to write the coordinates. So the same coordinate. The midpoint is considered as 0, 0, so that the bottommost edge is -1, -1. The topmost edge is +1, +1. And the left side edge is the +1, -1. And here the opposite corner is -1, +1. And if you consider the intermediate of 1 and 2 node, the 5th node, it is in negative coordinate of epsilon and negative coordinate of eta and 0th coordinate of epsilon. Here it is 0th line of epsilon. So 0, -1. Similarly, the 6th node, is 0th coordinate of eta and positive coordinate of epsilon. Here the node 7 is about 0th coordinate of epsilon and positive coordinate of eta. Here it is negative coordinate of epsilon and 0th coordinate of eta. So I am represented all the 8 nodes. This is child representation. The original parental representation. The original parental representation may be in different form of the rectangular element. We are considering some irregular curved boundaries from the node 1, 8 and 4. So the node numbering does not change 1, 2, 3, 4, 5, 6, 7 and 8. This is actual parental representation. In this we consider the child representation. So the n1 to n4 already we have derived the equation n1 to n4. We have derived the same equation. A small change is needed. From n1 to n4. I am writing the equation n1 is equal to 1 by 4, 1 minus epsilon, 1 minus eta. n2 is equal to 1 by 4, 1 plus epsilon, 1 minus eta. n3 equal to 1 by 4, 1 plus epsilon, 1 plus eta. n4 is equal to 1 by 4, 1 minus epsilon, 1 plus eta. So these 4 equations we have derived previously. So now I am going to derive the equation for n5, shape function 5, which is mid point between 1 and 2. So the scale factor into what are the equations we have to consider. If it is the midpoint, you have to consider all the other 3 sides from 263 and 374 and 481. All the 3 sides we have to consider. So I am writing the equation 263 multiplied by the equation 374 multiplied by the equation 481. So I am trying to write the equation 263. So what is the common factor here? Epsilon equal to 1 is the common factor. So I am writing 1 minus epsilon because If it is epsilon equal to 1, we can write 1 minus epsilon equal to 0. So that is the equation. We are making it as an equation. For equation 374, the common factor is eta equal to 1. So it is 1 minus eta. Similarly, for equation 481, the common factor epsilon equal to minus 1. So it is 1 plus epsilon. So I am going to simplify this. N phi is equal to S of 1 minus epsilon into 1 plus epsilon is equal to 1 minus epsilon square 1 minus eta. 1 minus epsilon square 1 minus eta. So I am going to calculate the value of scale factor here. For this we know N5 equal to 1 at node 5. The 5 has the coordinate of 0 comma minus 1. So apply the coordinate. 1 is equal to scale factor. So 1 minus 0. Here 1 minus of minus 1. 1 minus of minus 1. So it is scale factor into 2, which is equal to 1. So scale factor is equal to 1 by 2. Scale factor equal to 1 by 2. So after substituting the scale factor, the N5 becomes half into 1 minus epsilon square 1 minus eta. 1 minus epsilon square 1 minus eta. So I am keeping this is equation number 1 up to 4 from the previous derivation. Here it is equation number 5. I am keeping equation number 5. So I am going to derive for the other other 4 nodes. So again I am writing the nodes because it is easy to have the equation minus 1 comma minus 1, 1 comma 1, 1 comma minus 1, minus 1 comma 1, 0 comma minus 1, 0 comma minus 1, here 1 comma 0, 0 comma 1 and minus 1 comma 0, minus 1 comma 0. So this is the representation. Next N6, it is the similar scale factor can be arrived. So I am putting directly the scale factor. The equation considered for N6, it is 5, 6, 7, 8. So if you consider the 6th node, you consider all 3 other sides. So it is 1, 2, 3, 4. So equation 374 consists of same eta equal to 1. So 1 minus eta. 1 minus eta is one of the equation. Next 4, 8, 1 is having epsilon equal to minus 1. So 1 plus epsilon. The third side is having eta equal to minus 1. So it is 1 plus eta. 1 plus eta. So if you simplify this 1 plus epsilon and 1 minus eta square. 1 minus eta square is N6. N7 similarly 1 by 2. N7 means you consider other 3 sides 4, 8, 1. It is common factor of 1 plus epsilon. And 1, 5, 2, it is common thing of eta minus 1. 1 plus eta. And 2, 6, 3 is having common of epsilon equal to 1. So it is 1 minus epsilon. So we have 1 by 2, 1 minus epsilon square, 1 plus eta. It is N7. N8 is half into, you consider all 3 other sides. It is the common thing of eta equal to 1. So 1 minus eta. And this side it is epsilon equal to 1. So it is 1 minus epsilon. This side eta equal to minus 1. So it is 1 plus eta. 1 plus eta. So simplifying half into 1 minus epsilon, 1 minus eta square. So we have equation number 6, 7 and 8. All shape functions are found. One thing, we can't use directly the shape function of 1 to 4, that is N1 to n1 to n4 because it is applicable for 4 noded element. We have derived the n1 to n4 equation for 4 noded element. So we can't use it for 8 noded element. For that we can find n1 for 8 noded element. n1 for 8 noded element. Already we have the n1 equation for 4 noded element. So we are going to convert into 8 noded element. 8 noded element. So n1 for 8 node, which is equal to n1 for 4 node. You consider the node 1, the nearest node. We have to deduct the nearest nodal shape function. Nearest nodal shape function, and we consider half of the each shape function. Half of n5 minus half of n8. If you consider n1 first node, you have to deduct half of n5 and half of n8. Already we have n1 of fourth node. It is 1 by 4. 1 minus, now it is the first node, it is minus 1 comma minus 1. You can directly write 1 minus epsilon 1 minus eta according to the this representation coordinate. You can directly write 1 minus epsilon 1 minus eta. So now I am going to deduct half of n5. Half of n5. So half 1 by 2 1 minus epsilon square 1 minus eta minus half into half of n5 and n8 here. It is not n4, it is n8. Half of n8 1 minus epsilon 1 minus eta square. So the n8 equation is here. Kindly refer, and the n5 equation is in the previous slide. So now I am going to simplify 1 by 4 1 minus epsilon 1 minus eta minus 1 by 4 1 minus epsilon square 1 minus eta minus 1 by 4 1 minus epsilon 1 minus eta square. So it is possible to take 1 minus epsilon and 1 minus eta. After taking 1 minus epsilon 1 minus eta outside, here it will remain 1 plus epsilon, and here it again remain 1 plus eta. So in next step we are going to take out 1 minus epsilon and 1 minus eta. So I am keeping the first term as it is, 1 minus epsilon 1 minus eta for fourth node, minus I am taking outside of 1 by 4 of 1 minus epsilon and 1 minus eta. So the first term will remain 1 plus epsilon. The second term will have 1 plus eta. 1 plus eta. So if you combined 1 by 4 1 minus epsilon 1 minus eta minus 1 by 4 1 minus epsilon 1 minus eta into 2 plus epsilon plus eta. So from these two parts I am taking again 1 by 4 1 minus epsilon 1 minus eta outside. So 1 minus of this term, 2 plus epsilon plus eta. 2 plus epsilon plus eta. So finally we get n1 is equal to 1 minus epsilon 1 minus eta 1 minus 2. 1 minus 2 is minus 1 minus epsilon minus eta. Minus 1 minus epsilon minus eta. So this is the shape function. It is equation 9, actual shape function for 8 noded elements. Similarly, we are going to find out for node 2. Shape function for node 2. n2 for 8 node element. So n2 for 8 node, which is equal to n2 for 4 nodes. n2 for 4 nodes minus if you want n2, you have to deduct 6 and 5. half of 6 and half of 5. Half of 6 and half of 5. So half of n6 minus half of n5. So I'm going to write n5 first and n6 second. 1 by 4. The n2 of 4 nodes is 1 plus epsilon 1 minus eta. So just have some reference of minus 1 comma minus 1, plus 1 comma plus 1, and minus 1 comma 1 and plus 1 comma minus 1 for our reference. So for the node 2 it is 1 plus epsilon and 1 minus eta. So minus 1 by 4 I am writing for n5. 1 minus epsilon square 1 minus eta. Minus 1 by 4 I am writing for n6. 1 plus epsilon 1 minus eta square. So I am going to take all the parts. 1 by 4 1 plus epsilon 1 minus eta. So 1 minus, if I am taking 1 plus epsilon, here it will remain 1 minus epsilon 1 term, and plus if I am taking 1 plus epsilon and 1 minus eta, here it will remain 1 plus eta. So you have 1 plus epsilon 1 minus eta. So 1 minus 1 plus epsilon minus 1 minus eta. So it is minus 2 plus 1. I think it is eta. It is eta only. So it is eta. Here all common things. 1 by 4, 1 plus epsilon, 1 minus eta is common. So if you can deduct, it is 1 by 4, 1 plus epsilon, 1 minus eta, minus 1 plus epsilon minus eta. Minus 1 plus epsilon minus eta. So this is what n2 for the 8 noded element. Similarly, you can find n3 for 8 noded element is n3 for 4 node minus half of n6 minus half of n7.